like they're one machine. The third one, there's a good reason for that, and I'll get to that. Stick around. A few months ago, I did this with the M3 Ultra Mac Studios, and WWDC 2026 is right around the corner, and Apple may or may not announce an M5 Mac Studio. Nobody knows. So I'm doing the next best thing, clustering the M5 MacBook Pros, which is the closest thing to Apple's current top-end silicon you can actually buy today. And while I'm at it, I get to answer the question nobody else has run the numbers on. How much faster is the M5 Max cluster than the M3 Ultra cluster, head-to-head on the exact same distributed inference stack? Let me show you how I got there. Step one, before bothering with anything ambitious, this is always what you got to do with the cluster, is start out small. I needed to prove that the cluster actually wired up correctly and works. Thunderbolt mesh, 3 cables, RDMA enabled, a Jackal host file. What the heck is that? Well, I explained it in my other video. I also have step-by-step how to set this up on my GitHub. Basically, this is an MLX environment. MLX is the framework that runs on Apple Silicon to do inference and training and machine learning stuff. And you can actually run MLX distributed the way I'm doing here. So the environment has to match exactly on all these nodes, on all these machines. There are a dozen things that could go wrong. That's why the first couple of times I set this up, it took me a while. Now it's way easier. I have it documented, and I had Claude do it for me based on my documentation. Sweet. So I started with Qwen 3.4b, 4 billion parameter model. It's only 2 gigabytes. Obviously, this will fit on one machine that has 128 gigabytes. All 3 of these machines have 128 gigabytes, by the way. The whole point was, does it cluster at all? And yeah, it does. When you run it on one M5 MacBook Pro, you get 179 tokens per second. Pretty fast, right? But when you run it on 2 machines, you get 220 tokens per second. What? A 22% speed up? How? Well, that's what RDMA gets you. It's a huge win. I mean, this is a small model, so it's not a huge win for this model. But if we did use a larger model, maybe one that challenges the compute on each machine, then we'll see even better improvements. Here, there's barely any per layer work to share because it's such a small model, and the cluster pays some overhead for every layer that it shards or splits. But we're still seeing improvements in speed. And this is a proof of concept that the cluster is actually doing distributed work, not just sitting on one machine pretending. So the wiring is right, but a tiny model is the worst case for tensor parallelism, which is what we're doing here. Does it hold up when there's actual work to do? This is Qwen 3.5 122B A10B. It means active 10 billion parameters. So it's 122 billion, but it's a mixture of experts. On disk, it's 65 gigabytes, small enough to still fit on a single 128 gig machine. And that's exactly what I wanted because I needed to keep the one node baseline alive as control. On one node, we get 57 tokens per second. Quite usable. But on 2 nodes, we get 73 tokens per second, a 27% speed up. Slightly better than the small model. Now, mixture of experts models, or MOE models, don't scale linearly with tensor parallelism because the active expert size is much smaller than the total parameter count. So 27% is actually pretty good for an MOE. But more importantly, the chart now tells a coherent story. 2 nodes are reliably faster than 1, regardless of model size. Cool, the cluster is faster, but faster isn't actually the headline here. The headline is what the cluster makes possible. So what happens when a model is so large that it literally cannot fit on one machine? That's the biggest story here. Here we go. Same model, Qwen 3.5, 122B, 10A, A10B. Try saying that many times fast. But this is now the 8-bit quantization. On disk, that's 122 gigabytes. And it's right at the edge of what a single 128 gig Mac can actually hold once you subtract the OS and the MLX runtime overhead. And one node doesn't even load out of memory. You don't get a slow benchmark, you get nothing at all. On 2 nodes, you get 51 tokens per second. This is the moment the cluster goes from nice optimization to the only way to run this model at all. We saw this in the other video where I ran Kimi and GLM, huge models across this cluster. Here, the 1 node bar isn't just slower than the 2 node bar, it doesn't even exist. There's no number to put there. Okay, so 2 nodes opens up a door to a model that 1 node can't run. How wide does that door go? What's the biggest model 2 MacBook Pros can actually serve? Bigger model, GLM 4.7 4-bit, is 185 gigabytes on disk. This is definitely beyond what one machine can even hold. And it's not a benchmark toy. GLM 4.7 is actually useful. It's a coding grade model that people use for real work. Again, 1 node doesn't load out of memory. 2 nodes gets us 29 tokens per second. Pretty usable. It's not fast by Qwen 3.4b standards, but for a 185 gig model running on 2 laptops, that's legitimately impressive. It's well into the usable for real work zone. I consider this and write code with it. Open code, cursor, whatever you want to point at the OpenAI compatible endpoint. And I have videos on the channels on how to hook up different editors like VS Code and Zed to use local models. All right, if 185 gigabytes works at 29 tokens per second, can I push it even further? This one has been stumping people for a while since it came out, I guess a couple years ago now. Llama 3.1 405B, which is just 215 gigabytes on disk, but it's a dense model. The math says it should fit. 2 128 gig machines have 256 gigs of raw unified memory. And last time I checked, 215 is less than 256. So in theory, that should work. Well, I tried it. Look at that. That memory is going crazy. Oh. It is not happy. Both nodes wired up about 109 gigs of memory each, and then they started swapping. Holy cow. Wired memory is 42, compressed is 48. Swap used 21 gigabytes. So after about 25 minutes of CPU time, the benchmark hadn't generated a single token. The math lied. After OS overhead, after MLX runtime overhead, the KV cache, it just didn't work. Both nodes were technically making forward progress in CPU time, but at the rate where a single token would take minutes. Not usable. So here's the practical ceiling for a 2 times 128 gig cluster, about 200 gigabytes of model weights. Past that, you're swapping and thrashing. To go bigger than that, you need a 3rd machine or a 4th machine. First, quick definition, because they matter for the next 2 stages. And yeah, this is kind of a nerdy detail stuff that you might or might not care about. Basically, it has to do with the different kinds of parallelism. So yeah, get your nerd glasses on. Tensor parallelism, what we were using just now, that's what Jackal does. It slices each layer's weights horizontally and gives every node its own thin shard or slice. Every node runs every layer, but only on its own piece, and they constantly coordinate. So that's why you need fast connections. Then there's pipeline parallelism. You might have heard of a project called EXO. EXO does this, and this slices the model, each model vertically. Each node holds entire contiguous layers, and a token's embeddings flow through them one node at a time, like an assembly line. The difference between those two matters because tensor parallelism needs each layer's dimension to divide evenly, across all the nodes. Pipeline parallelism doesn't care. Here's the dirty secret of tensor parallelism. To shard a layer's weights cleanly, the layer dimensions, hidden size, intermediate size, attention head counts, all have to be evenly divisible by the number of nodes. And all the most popular and common models, Llama, Qwen, Mistral, GLM, Gemma, every popular model is built on a power of 2 dimensions. 4096, 8192, 14,336. Powers of 2 are divisible by 1, 2, 4, 8, 16, and so on. They're not divisible by 3. So a 3-node tensor parallel cluster works for almost no popular model out of the box. This is the actual reason this whole video is about 2 MacBook Pros instead of 3. It's not that I'm lazy, but I am kind of lazy. I'm having Claude do a lot of my work. So we're dealing with a fundamental property of how tensor parallelism interacts with how transformers are sized here. Now you might say, oh, Alex, so why don't you just get 4 MacBook Pros? Well, I do have 4 MacBook Pros. I still have my M4 Max, which I could have added to this experiment. However, we are now limited by the number of ports. Because of the topology, I'm using 2 on each machine for the interconnects for Thunderbolt, and the last port I'm using for Ethernet connection. So theoretically, if I had 4 Thunderbolt 5 docks, then perhaps I could manage this somehow, but I don't. So maybe next time. All right, so why do I have the 3rd one? Well, if you want 3 nodes, you have to switch parallelism strategies. You can still do it, but you'd have to use pipeline parallelism. Different stack, different bugs, different headaches. And I got these headaches trying to make this video for you guys, for you. I always get into trouble making cluster videos. I don't know why I do it. Anyway, there's a way out. You've heard of EXO before, and I've shown this on the channel before. They implement a couple of different strategies. They do implement tensor parallelism over RDMA for some of their models. And then they also, depending on your topology, also allow you to do pipeline parallelism instead. So I thought, okay, I'm gonna try it again. So EXO handles the pipeline parallelism plumbing for you. Gosh, that's hard to say. Who wrote this stuff? See, recommended for my cluster because my cluster only has one thing in it. But if I turn on EXO on another machine, it automatically scans and detects the other machine. And now we have 2 in the cluster. So the number of models and the kind of models that I can run increases. But all these, the ones that are grayed out, they're the really big models. Let's see if I can get to some of these. Although this one right here, I already have it downloaded. So maybe I'll just try this one. Gonna launch that, warming up, and it's ready. It's a small model. And I only have 2 nodes in the cluster right now. So if I start chatting with it, hello, boom. Hello, how can I help you today? And we're doing this at 105 tokens per second. All right, let's delete that. I'm going to launch EXO again on the 3rd machine, and now 3 machines are detected. So I have a total of 384 gigabytes of memory to share between models. Now if I go to load a model, I have more models available to me. I still don't have the really huge models like DeepSeek V3, GLM5, wow, that's a big one, and Kimi K2 and 2.5, which I did run on this before, so check out that video. Now I have to be honest with you, EXO is a little frustrating sometimes. And in my previous videos, I've shown the happy path because, well, it does work. It just takes a little while sometimes to get there, especially when models that you've already downloaded sometimes get re-downloaded when you query them. Even models that exist on disk, like this DeepSeek V3.2, which I have downloaded, and this Qwen 3.5 397B, which I have downloaded, it's grayed out for no obvious reason. Now, they're working on it, they're making it better all the time, but the issue where the model gets re-downloaded has been around for over a year. So I did try DeepSeek V3.2 first, 350 gigabytes, and I downloaded the whole thing, I copied it to the other machines, and EXO's manifest decided it didn't trust the file it had just downloaded. So then I switched to Qwen 3.5 397B, 6-bit, slightly smaller at 323 gigabytes, and EXO's manifest happily picked it up. However, right now, as I'm trying to make this video, it's not showing me that it's available for some reason. I don't know why. Even though there is a little green check mark there that says it's downloaded. But luckily, I saved my numbers from my previous run. Now, 323 gigabytes doesn't fit on one machine, doesn't fit on 2 machines. That's beyond the 256 gig pool we already established. But across 3 M5 Max MacBook Pros with pipeline parallelism, I got 28 tokens per second. That's not a benchmark stunt. That's a working 397 billion parameter mixture of experts running on 3 laptops sitting on my desk. And this is about the same tokens per second, roughly, that I was getting with GLM 4.7 on 2 nodes, which means going from 2 nodes to 3 nodes basically doubles the model size you can run at the same speed. In other words, tensor parallelism is much faster than pipeline parallelism. It's a real defensible trade-off though. Oh, and the head-to-head I promised at the start, on Qwen 3 4B, 2 M3 Ultra Max Studios got 170 tokens per second. 2 M5 Max MacBook Pros got 219 tokens per second. So that's 29% faster from laptops. When we put M5 Maxes into this body, if they do that, we might see a slight improvement. So it's less than an H100, but it's less power than my microwave, and it fits in the backpack. Repos are in the description if you want to check it out, and that video is right over here.